optimization? Ideas? What does it mean to optimize?
Like get the most out of something.
Okay.
So like maximum. It's kind of like maximize, but it could be minimized too. Just like.
Okay, so she said the most, like the maximum. Josh? What's that? But what does it mean to optimize? What does it mean to optimize? Change? No, something different than that. Yeah, the single best. Okay, and Autumn said there's kind of two, in different scenarios, there's two kind of cases of that for quantities, right? So if we want to optimize a quantity, what might that mean? What if it was profit? What would optimizing profit be? The best, the highest, right? The highest. And if it was, what's that? Casual, exactly. If we want to optimize casualties, say highway deaths, we want to get the least, right? Okay, so now what does that have to do with what we've been doing? So getting the highest value of a quantity or the lowest value of a quantity? What does that have to do with what we've been doing lately? Okay, relative max and relative min, right? Relative max and relative min. Okay, so let's look at this example, and let's just kind of do our best to work it together. We'll hash it out, and then we'll kind of we'll step back and kind of look at what the optimization process means in general. Okay, so this says an A-frame barn is to be built so that it's 30 feet high, 40 feet wide, and 60 feet long. Okay. A rectangular room is to be built inside the barn so that its ceiling abuts the roof. What dimensions should the room have so that its volume is as large as possible? Okay, so I'm just going to open this up and see if we can do this together. What's a good strategy for getting started on this? What's that? Okay, draw it. So is the description enough for you to have an image of it so you can draw it? So go ahead, see if you can do it. So an A-frame is basically like a triangular building. It's like a triangular building, okay? It has two roofs, one on each side, and it's like a triangle.
So is the 30 feet high? Would that be at the very
Yeah, the 30 feet then would be the height of the apex. The height of the apex of the roof would be the 30 feet, and the 40 foot would be the widest dimension at the ground. So compare your drawing with the person next to you, or put your heads together, see if you can come up with what this is describing. Because that's going to be part of these problems, is reading the text and being able to get a proper image. So that's not an A-frame. It's like a triangle. A-frame is like a triangle. It's not like the house you drew when you were a kid. Okay? It's not like this. It's a triangle. It just has two roofs. The whole thing is a roof.
It's like a teepee.
Yes, that is the wrong. And then inside, there is like a brick. There's a brick inside.
That's better.
Brick size of the room. Figure out the maximum size.
It's usually the best way to go.
Is that the wrong minimum of like 5 feet?
Oh, yeah.
So this is the start of it. So now what does the room inside look like? So says a rectangular room is to be built inside so that its ceiling abuts the roof. So it's a rectangular room with vertical walls and a horizontal ceiling that abuts the roof. So what will that look like? Okay, compare with the person next to you, see if you agree. Okay, so you said something like this. Is this what you got? Okay, so where does the actual problem or question come in? I mean, aren't we done? We've got this picture. Where does the question or the problem come into this? Connor.
Well, the issue is that as you increase the height, it's going to decrease.
You said
try and keep the roof at the top. So if you try to increase one of the dimensions, you have to find the optimal two values that would create the.
he's saying something about the fact that this width can change. Can this width change? And when, say, the width increases, in order for the roof to abut the height, the roof to abut the roof, the height would decrease, right?
The length doesn't matter. It's not necessary.
So like this, right? So there are many possible rooms that we could design in this, and so we're asking which one has the greatest volume. Okay, so what are we going to do? So what do we want to do? We want to optimize the volume of the room. So let's label some dimensions here. What was the height again?
30 feet.
The height is 30. And the width is? Okay, and so how come we're not showing the depth in this illustration?
Doesn't change.
It's non-changing. So you would just imagine that it's going to go back into the screen or back behind the board 60 feet, and that 60 feet is going to stay the same. Okay, in terms of everything, the room and the A-frame building. Okay, where do we go next? So what are we trying to optimize? The volume of the room. Okay, so if we think about using calculus to do this, the calculus that we were learning, then so what would our goal be then? What would our centerpiece of solving this equation, solving this problem be? We're trying to maximize the volume of the room. Related rates.
Make an equation relating all those related rates.
Make an equation. So we got lots of quantities that need to be related. This is true. Certainly making sense of how all the quantities are related to one another is going to be key. But what will be the centerpiece of this solving this problem? What's that?
Relating the area of the
Relating the area of the triangle to the area of the square. Okay? What do we have? So let's step back. What do we have in our toolbox of calculus that helps us get a maximum?
To find out the function equation of the area of the rectangle and to find the local maximum points.
Okay, he wants to get a function whose output is the area of the rectangle, and then we can look for a local or relative maximum of that function. What do you think?
Sounds good.
Yeah, that's it. That's right it. So what do we optimize? We optimize the output of a function, right? By finding relative maximum of that function. So this quantity volume, if we want to optimize volume, then the key is that we're going to need a volume function. Okay? As a function of what? Now. So this is gonna be the key. This is gonna be the center of this whole solving process. But as a function of what? What's that?
The rectangle.
Okay, the rectangle. A rectangle isn't a quantity, right? The input has to be a quantity. The rectangle is a shape. Well, okay, so, sorry. I'm using volume and area interchangeably here, right? Because the 60 is going to give us our volume from area. So do you want me to, sorry, should we call it, do you want to call it an area function? Or do you want to call it a volume function? It's the same thing, because volume is just going to include multiplying it by 60 deep, and area wouldn't. But in the end, we're just going to multiply by 60. Okay, so volume as a function of what? Yeah, Talia. Okay, yeah, so it's going to be a function of, the volume is going to be a function of something that's changing that gives us different volumes, right? So she wants it to be a function of the width. So let's split this in, so for ease sake, we can kind of split this whole thing in half by symmetry, right? So rather than have the quantity be the whole width, let's just look at that much right there. Okay? And so we'll call that x. And then what would the width be? The width of the rectangular bedroom. 2x, right? Okay? So what we need now is, what we're after is volume of this room as a function of x. So we need this rule, or this expression, that if we plugged x into it, it would give us the volume of the resulting room. Okay, so let's just start really generally here. So what will just a general formula for that volume be?
2x times 60 times
Yeah, width times height times length, right? So it'll be 2x times height times 60. So what's the problem with that? So what's the problem with this function in terms of if we need to optimize it?
height is not in terms of x.
Yeah, we need to get this all in terms of x. So here's where these, lots of related quantities. What do we need? We need a relationship between h and x. Any ideas? So here's our h right here. Here's our h. Here's our x. How can we get the relationship of h and x? Tell me, Pythagorean theorem. How is this Pythagorean theorem, h and x? Yes, actually, Pythagorean theorem isn't the way to go here. It's not. There's really. It's not going to work. Yeah, David. Daniel, sorry.
That's right. Perhaps similar triangles.
Similar triangles. I heard you guys say that up here. What? So
So you have the one similar triangle of the whole thing, which is the 30 tall.
30?
Which would be 20.
20.
Long. And then you have the smaller triangle, which is right next to the purple square.
right here.
Which is our h and our 20 minus x.
What? Yeah. So what is that dimension right there? He said. Well, we know this is x, and we know half of it is 20. So this and this 20. He said 20 minus x. You see that? So what he's seeing is that this triangle right here is similar to this one here, and that relationship of similarity can give us this relationship that we need between h and x. So what is it? Okay, so what would h over 20 minus x equal?
That's going to be the height, which is 30 over 20.
He wants this to be
Or
this
just 2/3.
2/3.
The height of the entire triangle.
So h over 20 minus x is the same as
3 2/2.
Oh yeah, 3/2.
30 over. Do you see it? So the similar triangles, and that relationship stays no matter how we change x, right? That will always have this side of the room will always form a similar triangle, similar to this triangle that's half of the whole A-frame. Okay, what now? Yeah, so what we needed was this as an expression of x, so that we could have our volume all in terms of x. So what does h equal? This is 1.5. 3/2 is 1.5, right? Times 20 minus x. So we can take that, and that's always h. So we can substitute it here for h. What do you think? So I think this is 60 times 3. Is that 180? 180x times? Okay, and if we wanted, we can multiply that out. What is it?
3,600.
3,600
X
x.
minus 180 x.
Okay, what now? So what does this function do? What's the input into this function? What's the input into this function?
Half of the width of the room.
Yeah, from the center out to the edge of our room, right? From the center or half of the width. And if given us particular value of that function outputs
The volume.
the volume of the resulting room. So what do we want to do?
Take the derivative. Find where the first derivative is equal to 0. So you can find the
He wants to find where the first derivative is equal to 0. Why?
That's where it's going to have a maximum. Or that's where the rate is going to pause for a minute.
Yeah, so why does the first derivative equal 0 give us potential value of maximum?
Because the rate of change is going to either go from climbing,
Uh-huh,
go either climbing to shrinking,
Right.
the other way around. So
right?
it could potentially accidentally give us a minimum.
Okay, so this setting the derivative equal to 0 gives us critical points where we could get, or? Yeah, okay. So we're looking for, we know that at maximum and minimum, what does the function do? Pauses, right? Pauses. So that's why we set the first derivative equal to 0, because we want it where the accumulation doesn't change for a moment. That's going to be potential location of a maximum, or minimum, where the accumulation doesn't change or pauses for a moment is those high and low points, but then also these types of points too. We didn't really have a name for it. Do we have a name for it? Maybe a rest stop. When all of them rest, right? All of them rest. But a rest stop, it's kind of like it's going up, it takes a moment rest, and then keeps going up. Or same thing with going down. Okay? So we're going to take this. We want to know, where does the volume pause? At what value of x does it pause? 10. Okay, so we know that at x equals 10, we get the maximum volume, right?
Not necessarily.
Not yet, right? It could be a minimum, it could be a rest stop. Okay, so what can we do? There's different ways we can show for sure that that is maximum on them.
You could look at all the different values and then plug each one in and then find the greatest volume, but that's probably
A little too much work, okay. Is there another way? Sharon, is there another way that we can confirm that this will give us a maximum? Yeah, that's kind of sidestepping calculus altogether, though. That's true. Yeah, that's true, absolutely. Well, how can we use calculus? What did we learn about?
You could take the second derivative and see if the slope of the rate is increasing.
Okay, and what do we want it to be? At a maximum, we want the rate to be? Rate is decreasing, becoming less positive and more negative, which means the second derivative should be less than 0. Rate is decreasing. Does that give us a max? Yes, that gives us our max, right? The rate is decreasing, becoming less positive, more negative. Therefore, if there's a 0 first derivative along with a decreasing rate, it has to be a high point where it pauses. Okay, so x equals 10 means, what about, that means the width is 10, right? No, the width is 20. And what's the height? How can we get the height? Here's our relationship of x and h. All we have to do is put 10 into this. It tells us what the corresponding height is. 15. And how do we get the volume? Yeah, we could take these two multiplied by 60, or we could go back here and plug our 10 into our volume function. Either way. Okay, any questions on this? All right, so I want to give in the last 5 minutes, I want to kind of give a crash course on angle and sine and cosine, because lots of these optimization problems deal with quantities of angle, sine, and cosine, like in circular type situations. So I want to give kind of a crash course on that. Any questions on this one? Okay, so I'm showing you, so I'm going to do this fast, okay, so we can get through it. I'm showing you 3 circles here. I'm showing here the radius of the smallest circle, right? So I'm going to take that radius, and I'm going to peel it off and wrap it on its circle. Okay, so how long is that arc right now? It's 1, right? Because it's the same as the radius of that circle. Okay, so the next circle has a radius of 4. I'm going to peel off its radius and lay it on its circle. How long is that arc? 4. Okay, Same thing with the 6, radius 6. I'm going to peel it off, put it on its circle. It has an arc length of 6, right? So clearly what's different about these 3 arc lengths is their linear measure. Their linear measure. This one's 1, this one's 4 units long, this one's 6 units long. But what's the same about them all?
The ratio of their length to the entire length of the circle. I'm sorry, the entire circumference.
Okay, he's saying they all have they all give the same fraction of 1 full rotation or 1 circumference. Do you see that? Okay. Okay, so and the end of the arc all lie on the same. They all create the same angle, right? They all create the same angle. Okay, so although this is this has length 1, and this has length 4, and this has length 6, they all have a length of 1 radius. Okay, they all have a length of 1 radius, and so this angle measure, equals 1, what we call radian. So the number of radians is equal to the number of radius lengths that the angle cuts off. So no matter what circle you pick, it's always gonna cut off 1 radius length. So that's why this angle is 1 radian.
There are 2 pi radians per circle.
That's right. Okay, so now I'm going to show so here's 1 radius length, here's 1 radius length, and here's 1 radius length. See, I'm marking off on the smallest circle. So how many units long is that? That's 3. Okay, so for each one of these, each blue, purple, blue, and red, I want you to find S, R, and theta. S is the linear measure of the arc. R is the radius of the circle. Theta is the angle that's cut off by that arc. The angle that cuts off that arc. Okay? So for all 3 of them. So S, R, and theta for the blue, and S, R, and theta for the red. Go, quick. S is the arc length in the units of the scale. S is the arc length in the units of the scale. R is the radius of the circle. Theta is the angle in radians that subtends that arc, or cuts off that arc.
For all 3 of them?
Is that a question? Okay. Okay, how long is the purple one?
3.
What's the radius? How many radians is that angle? 3. Okay. Length of the blue? 12. What's the radius? What angle does that represent, that blue arc? 3 radians. Okay. Length of the arc? Radius? Angle? Okay, so what's the relationship between S, R, and theta? S equals.
Oh, you want that one. R theta.
Okay, and why does this make sense? Because this is the radius. And what does theta represent? The number of radius lengths that the angle cuts off. So this makes perfect sense. You're just taking the length of the radius times how many radii you have. And that's the total length of the arc. Okay, so that's a really important relationship. And it makes sense when you think of the angle as number of radius lengths of the arc that angle cuts off. Okay, one more thing. So what is the sine and the cosine? Okay, so this is our angle of 1 radian. Okay, this is 1 radian. For the terminal point of the arc, then, it has coordinates, x and y coordinates. Okay, so what do you approximate the x coordinate to be about there? About 0.85? And what about the y coordinate? About 0.55. Okay, what are the units of those? So what unit is 0.85 and 0.55? Isn't it radius lengths? It's 0.85. So here's the full radius. We're at the y coordinate is. Let's screw that
Yeah,
up.
they're backwards.
Thank you.
Use the y-axis coordinates.
Is this right now?
Yeah.
Okay, so here's the full radius length. Right now the y-coordinate is 0.85 radius lengths. Do you see that? And here's the full radius length out in the x direction. Right now the x-coordinate is 0.55 radius lengths. Okay, so this is called the cosine. The number of radius lengths that you are to the right or left of the vertical diameter. And then the sine is the number of radius lengths, the y-coordinate, or the number of radius lengths up, or number of radius lengths down of the angle. So these are approximations for the cosine of 1 and the sine of 1. Okay, so the homework for Wednesday is it's problems from the book, but you're writing them out on paper, so it's not my math lab. It's a little bit longer, so you got to start tonight. So you're going to spend both nights working on it because it's a little bit longer, but you need to kind of dig in and work at them so that we can, when we regroup on Wednesday, it'll really make sense. Okay? Yeah. If you want to, I'll show you how to access it. If you want to stick around a second.
Yeah, that's why I don't
Because I went to YouTube.
Okay, so is anybody interested in knowing how to access the book online? So you know this website here?
Yeah.
So what I do is I go to Multimedia Library. You can also try interactive ebook, but I go to Multimedia Library. It's the second to last one. And then I just click on the textbook. And then it just shows up below here. So you're going to be in chapter 4, 4.3 and 4.4.
Okay.
So like if you want the problems from 4.3, you click on 4.3. I'll go back and show you again. Okay. So I click on, you can do either interactive ebook or multimedia library.
You need to get the Wolfram reader thing.
Right. If it's not working, you go back to the home page and you got to do the browser check.
Oh yeah, you can just do the browser.
If you do the browser check here on the main page, it'll tell you what you need to get everything working.
And is it like plugins and stuff that you can
It's plugins.
Oh,
Yeah, and they're all free. They're all free.
I went and downloaded an EXE, like a setup, and had to
Yeah.
install something. I guess you could do
But then you go to, like I said, Multimedia Library here, then select Multimedia Textbook, and then Find Now, and then it just comes up here.
And you said it's 4.6?
No, 4.3 and 4. So if you click on 4.3, it'll come up, and then you go to Exercises, Most of them are in the basic skills.
Okay.
Okay?